So now that we've talked about various principles of reactions, we can actually look at some examples of reactions. The SN1 reaction is a very prototypical nucleophilic substitution reaction. Okay, that's what the SN stands for, nucleophilic substitution. 1 indicates that the mechanism is unimolecular. I'll describe what that means in a moment. SN1 reactions are, again, nucleophilic substitution reactions. They involve a carbocation intermediate, and they usually only happen with secondary or tertiary alkyl groups. So they pretty much only happen when you have a highly substituted carbon atom, secondary, tertiary carbocation. Okay? Because they form a carbocation, you need to have them be stable, so they need to be secondary or tertiary, highly substituted. Here's a summary of the reaction. My chloride group comes off as a leaving group. Water comes on, it adds hydroxide as the nucleophile. So let's look at this reaction overall. The first step is the carbocation formation. So my first step is the leaving group just comes off and results in the formation of this carbocation. The second step, now that I have a carbocation, this water, which is a very weak nucleophile, can come back and attack onto the carbocation, and that will become deprotonated and ultimately form my alcohol group. Okay? So this is a two-step process. The reason why we call this unimolecular, why it's an SN1, is because the rate determining step, that's this step, is the slowest step, only depends on the concentration of that one molecule. The rate determining step only depends on one molecule, and so we call that unimolecular. It basically just reacts on its own. It's not reacting with anything else. It's the rate determining step, so it determines the rate law of the overall reaction. It just depends on that one molecule, so it's unimolecular. SN2 reactions, also nucleophilic substitution reactions, do not go through a carbocation intermediate. It's a 2 because it is a bimolecular mechanism, and I'll describe how that looks in a moment. Here, because we don't have a carbocation forming, we require a strong nucleophile. So the nucleophile has to force off the leaving group. The other part of this issue is that because you have to have the nucleophile actually come in and attack the electrophile, there can't be steric hindrance. If you have a lot of steric hindrance, these big, bulky groups like this, then the OH simply can't get access. The nucleophile can't access the electrophile, and so you won't get a reaction. So this will largely only happen when you have mostly unsubstituted, in this case, a primary halide, alkyl halide. So the nucleophile doesn't have a lot of resistance when it comes in and attacks. There isn't a lot of steric hindrance here. So this mechanism, you can see the nucleophile comes in, attacks the electrophile. It happens as a single step this time. You can see our transition state here. And it just pops off the leaving group. So notice the nucleophile here attacks directly. Because of that, because it doesn't go through a carbocation intermediate, if we look at the summary here, SN1 reactions, they normally happen with more bulky, more stable carbocations because the bulkier groups limit the SN2 reaction from forming. The SN2 reaction occurs with less substituted alkyl groups because they have unstable carbocations. They require strong nucleophiles. And because of the number of steps in which they happen, that is, SN2 reactions happen as a single step. The nucleophile directly attacks the electrophile. You can see I'm always going to end up with this one stereoisomer. So if these had been chiral, I would end up with the enantiomer. It inverts the stereochemistry because it attacks from the back side, and I'm almost completely going to get one enantiomer. because it can only attack from that one side. It's too sterically hindered from the chloride side because chloride's big. The SN1 reaction, though, this nucleophile can attack from the top or it can attack from the bottom. Both of those are perfectly fine. And so, largely, with SN1 mechanisms, you end up with a racemic mixture. And so that's another way to differentiate what kind of product you might get. Okay? Or what kind of mechanism occurred based on the products you got. So now we've talked about these foundational principles of reactions. And what I want to do in this last section is to cover some generic types of reactions in organic chemistry. This list is mostly complete in the sense that there are theoretically other reactions that could be tested, but these lie at really the core, the foundation of where you'll see a lot of reactions occurring. Now, I'm going to summarize all of this and the importance of this lecture at the very end. But for now, I recognize that we're going to talk a lot about more specific reactions and different functional groups and all that in the next organic chemistry lecture. So this one is largely a foundational lecture. We'll, again, summarize that at the very end. So a review of oxidation numbers really quickly. Remember, we talked about this in Chemistry 5. The different oxidation numbers, like H, Na, these are going to usually have an oxidation number of +1, oxygen usually -2, or halides -1. And so in organic molecules, we can identify the oxidation state of different molecules. Okay? We can do that for inorganic molecules, like the ones you see here, and we can do it for organic molecules. But it actually gets pretty tricky when we start talking about redox reactions for organic molecules. So we're going to start to look at that in a moment, but let's take a look at this practice problem. Okay, so the modified caffeine molecule, how many formal charges are present on this molecule? Well, the fact that we're being asked about formal charges should tell you that they're not going to draw them for us. Right? They're not going to be that generous and just have us count how many pluses and minuses there are. We're going to have to evaluate each atom and decide whether it's going to be charged or uncharged. If I look at all the hydrogen atoms, they all appear to be fine. There shouldn't be any hydrogen atoms that are charged. The oxygen atoms appear to be okay. There's no carbocations. All the carbon atoms are fine. The charges, if there are any, should be on the nitrogen atoms. And nitrogen typically wants to form 3 bonds. So here's a nitrogen with 3 bonds. Here's a nitrogen with 3 bonds. Those are fine. This nitrogen only has 2 bonds, so I should have a negative charge here. And this nitrogen has 4 bonds, so I should have a positive charge here. Now, note, the question does not ask what is the net charge on this molecule. The net charge is 0. It asks specifically how many charges are present. 1 positive and 1 negative. There are 2 charges. So our answer then here is C. So oxidation and reduction reactions for organic molecules. Like I said, it gets kind of tricky when I want to figure out, did the oxidation number increase or did it decrease here when the hydrogen atoms were lost? Kind of convoluted to figure that out. There's an easy, dirty trick to determining whether oxidation or reduction has occurred for organic molecules like this, or anytime you have oxygen and hydrogen atoms. And the trick is, when you add bonds to hydrogen or get rid of bonds to oxygen, lose bonds to oxygen, that is a reduction reaction. So adding hydrogen atoms and or removing oxygen atoms or bonds to oxygen atoms is a reduction reaction. Oxidation occurs when you remove hydrogen atoms and or add oxygen atoms. So let's take a look at some common functional groups and the redox reactions that can occur with them. Carboxylic acids are very highly oxidized. Okay? This carbon atom has 3 bonds to an oxygen. So that's about as oxidized as you can get. We can reduce it down to an aldehyde. You can see we got rid of one of those OHs. We got rid of bonds to oxygen. We can reduce it even further to an alcohol. You can see we got rid of even more bonds to oxygen. We added a whole bunch of hydrogen atoms here. So those are all reduction reactions. Oxidation would be the reverse. If we're looking at ketones to alcohols, okay, reduction of a ketone would give me an alcohol. Oxidation of alcohol would give me a ketone. Okay, common oxidizing, common reducing reagents or agents. Common oxidizing agents, you should recognize all of these as oxidizing agents. And surprise, surprise, all of our oxidizing agents have oxygen in them. Even PCC, considered pyridinic chlorochromate, has oxygen in it. Reducing agents, you should recognize all of these as reducing agents. They all have hydrogen in them. And so they'll all be able to reduce compounds. Again, surprise, surprise. So we can largely tell just by looking at the structure of some reagent whether it would be a reducing agent or whether it would be an oxidizing agent by its presence of oxygen or high concentration of oxygen or high concentration of hydrogen atoms. So with that, let's try this problem. Okay, so NABH4 is a strong reducing agent. It's most useful for which of the following reactions? Aldehyde to carboxylic acid, alcohol to carboxylic acid. Note, this is going to be an oxidation reaction. We're adding bonds to oxygen atoms. This is an oxidation reaction. Ether to epoxide is also an oxidation reaction. We're going from an ROR to an ROOR. That is, we're adding bonds to oxygen. The only one that's actually a reduction reaction is the ketone to the alcohol. We can see that here. When we go from the ketone to the alcohol, we add hydrogen atoms. We're adding 2 hydrogen atoms. So this is a reduction reaction.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than exam crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.